Welcome back to Mechanical Systems Design. In this video, we'll discuss mass-efficient design, and we'll mostly do one long exercise, so it'll be especially important to have read the topic reading and to have pencil, paper, and a partner. So up to this point in the class, we've mostly discussed analysis. Given a thing like a candidate design, tell me an outcome like factor of safety with respect to a certain type of failure. In design, we're going to flip those. Given a desired outcome, like a factor of safety and minimum mass, tell me what thing would achieve it, like the geometry of a component. And whereas analysis is relatively monotonic, you follow a set of steps, you get an answer, maybe there's one correct answer. Design is deeply iterative. There's no one right answer, and there's no set of steps that's guaranteed to find it. Instead, you have to guess at good designs and then analyze them and then learn what you can from that analysis to make better guesses as to an effective design. And of course, to be good at that, you need to be really good at analysis. The faster you can do analyses, then the more candidate designs you can consider in a set time. And the better you are with those analyses, the more you'll learn and inform better guesses as to candidate components. But analysis isn't enough. We also have to engage in this iterative process. And so it's helpful to think about our approach. And there are many such processes in mechanical systems, but one that comes up often is design for mass efficiency. And it's a good study case to talk about this approach. And I like to think about mass efficient design as an optimization problem. We have constraints that we need to meet. We have parameters where we can choose anything we like, and we have an outcome we're trying to maximize or minimize. And in the case of mass efficient design, our constraints include loading, material, manufacturing, and factor of safety. And when we look at a bigger problem, we might relax some of these or see interactions like loading might be influenced by other components in an assembly, or we might choose different materials or manufacturing processes. But when designing a single component, it's useful to treat those as fixed. Then we have our free parameters, and that is part geometry. We can choose anything we like, both qualitatively and quantitatively in terms of the values of those dimensions. And our outcome in this case is mass, which we'd like to minimize. When you first start on this kind of problem, it can be daunting. You've got a blank page and literally infinite possible answers, some of which will be good and some of which will be bad. So what do you do? Well, this is the process that we'll use. First, we'll generate candidate shapes using sketching, cataloging, low fidelity prototypes, or even generative design tools in CAD. We'll pick one. And when we do this, we're going to try to keep things simple. So simple shapes that are defined by a very small number of parameters. You can learn a lot even from very simple shapes. And as we go through this process, we'll try to explore a wide variety of shapes without increasing complexity. So how many qualitatively different ways can you accomplish the task with very, very simple shapes? Then we'll pick one and we'll analyze it. And this is where we'll apply free body diagrams, stress and buckling analysis, any other failure analysis of interest. And the kinds of problems that we'll run into there are similar to what we've seen already. We might not be sure about the loads, the reaction forces, or the qualitative stress model to use, things like that. And when we run into those problems, we'll try making simplifying assumptions, and we'll check them using static equilibrium, deformation, and finite element analysis sketching, which we'll go into a little later. We'll then optimize. We'll invert our analysis and solve for the value of a geometric parameter that will exactly match our factor of safety and thereby minimize mass. And we'll look at how we can change the remaining parameter values to minimize mass as well. And finally, we'll test our parts using either high quality finite element analysis or experimental tests of functional prototypes. And as we go through this process, we'll learn a lot, and that will guide us in making new guesses about candidate shapes. And as we become expert in this process, we may jump off at earlier points or go back not all the way to the beginning. For example, we might see from a free body diagram that a certain choice has led to a very high reaction force, which may be bad. And then we might go back and choose a new shape. Or we might see in our high quality finite element analysis that we've made a wrong assumption about loading, and we might jump back to our free body diagrams. Okay, so that's the process at a high level conceptually. Let's learn more about it by applying it to a real world problem. And here we have a very simple mass optimal shape problem. And in this scenario, we have is some point here to which we need to apply a force directly downward with magnitude F. And that point needs to stay right where it is. So it's probably going to be on our component. And down here we have the ground, which is assumed to be infinitely strong and rigid. And we're going to design a component that connects that point to the ground such that when the force is applied, the component doesn't break and the point doesn't move too far. So the first step in this process is to generate some ideas for candidate shapes. So what I'd like you to do now is get out your paper and pencil and for 1 or 2 minutes independently, draw some ideas about what a good part shape might be for this scenario. And then discuss with your partner for a minute or two and then come back. So keep in mind that we'd like these candidate shapes to be as simple as possible while covering a variety of qualitatively different shapes. And for our purposes here, I'd say at least 10 different shapes. And then after you have some on the page and you've discussed them, maybe pick one that you think would be a good candidate for this scenario. All right. So I'm going to hit pause now, come back when you're ready. All right. So hopefully you've had a chance to sketch out a few different ideas and discuss them with your partner. But for our purposes here, it would help if we had one concrete design to look at. So let's imagine that this was one of your candidate shapes. And who knows, maybe it was. Let's analyze it and continue through our process. So the first step in analysis is to draw a free body diagram of this component, load analysis. So now what I'd like you to do is sketch out your FBD, take a couple minutes to do that, then compare notes with your partner and discuss, and then come back. And so you can hit pause now. All right, so maybe what you saw as you tried to develop your free body diagram is that because these legs are glued to the ground with magic glue, we have all possible forces and moments at those reaction points. And so our problem is statically indeterminate. And this is something we run into very commonly in these mechanical design problems. So when you see that, the first thing you should think is maybe I can make some simplifying assumptions. And that's where all the trick is in this free body diagram problem. So if you haven't done so yet, I'd like you to pause now and discuss with your partner what are the best simplifying assumptions for this FBD. Otherwise, we're going to take a look at one candidate assumption and then we'll check it to see if it's okay. So here's one assumption. You might think perhaps those reaction forces at the feet point straight along the legs, right along the centroid. So is this a good set of assumptions? Well, we can find out by applying our checks. And the first check, of course, is static equilibrium. Then we'll do deformation and FEA sketching. So first, what I'd like you to do is take a moment and write out your static equilibrium equations for this component with this FBD and see if it's possible to achieve static equilibrium. All right, take a minute or two by yourself, then a minute or two with your partner, and then come back. You can hit pause now. All right, so hopefully, once you've made some assumptions about the forces, the equilibrium equations aren't too bad. They're pretty straightforward. And we'll see that, yes, it is possible. So if we look at the sum of the forces in the y direction, we're going to see that they need to be 0 or this thing would accelerate. And we have a force downwards of F, negative F, and then 2 y components of our 2 foot forces, F1 cosine theta plus F1 cosine theta. And here, notice that we've had to define a geometric parameter in order for this stuff to make sense, and we're going to collect those as we go through our analysis. So we're saying that the angle from vertical of the legs is theta. So that means that this axial force on the legs is F1 is F over 2 cosine theta. Then we need the sum of the moments about any point we choose to equal 0. And when we do moment balance, it's always nice to pick a point through which lots of forces go, because then they have no lever arm and they don't contribute. And it turns out that if we pick this point up here, all 3 forces pass through it. So we see that the lever arm for each one is 0, and the sum of the moments about that point is always 0 if we've chosen the correct line of action of our reaction forces. And then finally, we have a check on the sum of the forces in the x direction. And here we have implicitly assumed symmetry by saying these 2 forces are the same. So then in the x direction, we have F1 sine theta minus F1 sine theta is 0. And that's always going to be the case. Okay, so this is looking good. We can achieve static equilibrium. What about deformation? So here, what I'd like you to do is draw a sketch of the deformed shape once this load is applied. And then we'll see if that deformed shape is consistent with our assumption about the reaction forces. And the way I like to do this is first think about what's constrained. And in this case, the bottoms of these feet will be fixed. They won't be able to move, and they won't be able to rotate because they're glued to that ground. And then think about what do we know about how it will definitely move. And in this case, if we push down here with a force, this point should probably go down. So usually you'll see that if you push on something, there's at least a component of the movement in the direction that you pushed. And then try to draw a deformed shape that's consistent with those things. And remember that when something deforms, the whole thing can stretch or compress or bend, but this is all one solid piece. It's not made of sticks and hinges like a truss. So you wouldn't, for example, see the leg rotate at that point or the top of the V rotate. Instead, things have to gradually change their angle or their length. All right, so take a moment and try to sketch the shape of this inverted V once it's deformed by this load. And you can exaggerate it to make it more visible. Spend a couple minutes on that by yourself, discuss your answers with a partner, and then come back. And you can hit pause now. This analysis can be a little tricky for people who are just getting started and still developing intuition. But don't worry if that's the case. As you do more of these and look at more FEA results, it'll start to come together for you. So here's my version of the deformed shape. And first we have here the undeformed shape as a dashed line. I like to draw these as stick figures. I find it a little easier to sketch. And here is the deformed shape. And here's why it makes sense. So first notice that the feet there have not moved, and the angle of the legs at the feet is consistent. So we're acting like solid material instead of a hinge. You'll notice that the point of load application has moved in the direction of the load, which is something we would expect, and that the angle of the top of the V is preserved locally, though we have some deformation as we go through the part. And it turns out that this deformation pattern is consistent with our guesses about the reaction forces. And here's why. You'll notice that the length of this leg has changed a lot. So I'm denoting the axial displacement as delta A, and that's big. And the displacement orthogonal to the centroid here is small. It does have to displace a little bit, but it's much smaller than the axial displacement. And if you stretch something a lot, that means that you're straining the material a lot. And if there's high strain, there's high stress. If there's high stress, there's high force. So something deforming a lot in a direction is an indication that there's a big force in that direction. Now, how do we know that the axial force is big compared to the bending force. Well, one is the size of the displacements. It's also true that the stiffness in the two directions will be different. This thing will be much stiffer in the axial direction than in the bending direction. And you can kind of prove this to yourself if you take a pen or pencil and if you push on it really hard, try to get it to shorten by 1/4 of an inch or centimeter. That is pretty hard to do. But if you bend it, you can pretty easily get it to deflect 1/4 of an inch or so. So both of those factors, smaller displacement and lower stiffness in bending, suggest that orthogonal force will be small compared to the axial force. So this is a reasonable assumption. Now, what if you're not feeling too confident about that? How can we check it? Well, let's use a finite element analysis sketch. So if we just quick whip up the qualitative shape, not paying too much attention to dimensions, just the relative size of things, and run FEA, we can get an answer as to what we really expect those reaction forces to be by showing resultant forces. And let me show you how to do that real quick in SolidWorks. All right, so this is that T part that we used in a previous video, and it has these fixed hinge constraints in these two holes. I'd like to see when I apply this force down here, what are the reaction forces at those two holes? So what I can do is come over to results, right click, and click list result force. And now I'm going to select those two surfaces that were constrained. This is a little annoying in wireframe, so let's switch over to solid. So I've selected the interior surfaces that were constrained. Then I'll select display resultant force and update. And you can see now we have these reaction forces appear on our screen. And you know, their point of origin isn't necessarily meaningful, but the direction of the force and the magnitudes that are summarized here is the integral of the force over that entire surface. All right, so we've done that for our inverted V, and this is what we got, that the reaction forces look like they're pointing pretty much along the centroid of these legs. So another verification that our guess at the free body diagram is good. We can also see that looking at the stress analysis result from FEA. If you look at the pattern of stress in these legs, it's consistent with axial loading. It's a nice even color all the way across the cross section, which is what we expect when we have axial loading. If we're bending, then we would expect higher stresses at the edges and low stress in the middle, or at least a strong variation in stress as you go across the cross section. We don't see that. So yet another validation of our assumption about the forces. Okay, so next we're going to analyze the component for stress. And what we'd like to do is pull out the relevant stress equation, break our component into chunks, do a new free body diagram for each chunk, and be sure to cut where you're going to estimate the stress. Then pick the correct model and write down an equation, stress equals something, and it should include some of your geometric parameters. All right. So work on that independently for a couple minutes, then compare notes with your partner, and then come back. And you can hit pause now. All right, this one is fairly straightforward. If we break this V into 2 bars, then those 2 bars we'll see become 2 force members. So we've got F1, which we solved for before, that's going up and to the right. Well, at that top cut, we must get another force that's equal and opposite in magnitude and collinear with the first if we're to have static equilibrium. So that means that this whole leg is experiencing axial compression. And let's say we want to find the stress in the middle. It doesn't matter too much in this case because it should be uniform. But we cut in the middle, we do a new free body diagram, looks exactly the same, F1 up to the right, F1 down to the left. And the stress is going to be that force, that axial force, divided by the area. And so I'm going to have to define a cross section. And in this case, you might have done this differently, but I said, hey, let's keep it simple. by making it a square. So it only has one dimension that defines it. And so in that case, the stress due to axial compression would be the applied force divided by 2 cosine theta times a squared. All right. Now, something else that we should be worried about for this component is buckling. So now take a moment and write down the buckling equation for this case. You should have a critical force in terms of geometry and some other things. And so take a couple minutes, work that out yourself, compare notes with your partner, and then come back. And you can hit pause now. All right, so this starts relatively easy, but then it gets a little bit tricky. So writing down the main equation is straightforward. We can just copy this over from our notes. The critical force is equal to this constant times pi squared times the elastic modulus of the material times the area moment of inertia of the cross-section divided by the length squared. And the area moment of inertia, we can get that for our cross-section. L squared, well, let's see, L is going to be this distance, and that's going to be a function of the height of the V. So how high was that applied force off of the ground? We'll assume that we can't change that. So we'll call that H. And we're going to be able to get L as a function of H. But C is a little bit trickier here. So if you haven't wrestled with this yet, take a moment and think about which constant, buckling constant, should we use in this case. And remember, that's a function of what the boundary conditions are, what the constraints are on the ends of this beam, of this column, as it's buckling. So if you haven't done that yet, pause and think it through and then come back. If you have done it, it's an interesting, tricky one. So if we look at our table of the typical buckling constants here, there are a few things that might jump out at first. We're going to skip this first one because the bottom is pinned, and in our case, we know that the bottom of that leg is fixed to the ground. This one could be something to consider. So you can imagine that the base of the leg is fixed to the ground, and the top of one of the legs is kind of constrained by the other leg to keep it from rotating a lot. So maybe it looks like this, in which case the constant would be 4. But there's another way that it could buckle that's more pernicious, and that is this fixed free condition. So when we look at these buckling problems, we're prone to thinking about them in the plane that we are looking at. But very frequently, out of plane is more dangerous for buckling. And that'll prove to be the case for this example as well. And so you can imagine if we're looking at this from the side, at the V from the side, the tip of the V could tilt off to the side, and that would result in a constant of 1/4. And 1/4 is a lot smaller than 4. So if that is a viable mode, then the resulting critical force would be lower, and then that would happen first before this kind of buckling occurred. So let's go with that for now, and we'll check ourselves in a moment. So if we come back to our critical force equation and substitute everything in, we'll have C is 1/4, I is 1/12 a to the 4th. That's just, we look up the value in the table or use that for a rectangle. The height we know will be L cosine theta. So L squared, which we need to put in the bottom, will be H squared over cosine theta squared. And if we plug that all in and massage it, we've got the critical force is pi squared E a to the 4th times cosine theta squared divided by 48 H squared. Okay, so we have our buckling equation. Let's double check in FEA with our quick CAD sketch. Well, when we run the buckling analysis, it's the first mode that appears with that has the lowest load factor. That is the lowest factor of safety. And indeed, it is that out of plane pattern we were talking about. If we scroll through modes, eventually we'll find this one, which looks kind of like the other mode that we talked about, fixed. But this happens at a much higher load factor, about 10 times higher than the other one. So we chose one right. Okay, so now we have the correct we've got a good free body diagram for our part. We've got a good simple stress analysis and buckling analysis for our part. Now we can do is invert those analyses to solve for the value of a critical geometric parameter. So what I'd like you to do now is take this equation here, and you're going to substitute in something that has factor of safety, and then solve for one of the geometric parameters. And at the end, you should have that parameter equals some function of the force, the factor of safety, maybe other parameters. And one of the tricky things here is to choose which parameter you solve for. And in this case, you should choose one for which mass will uniformly increase as that parameter increases. So the simpler the relationship between that parameter and mass, usually the better. Although we can always correct this later, it just makes the algebra messier. So take a moment, solve for your chosen parameter, and write down the equation for what its value should be to exactly match your factor of safety. Then work on it with partner, then come back, and you can pause now. All right, so the first step is pretty straightforward. We're going to substitute the yield strength over the factor of safety for the stress. That's what we want the stress to equal. And if it does, then we'll get our factor of safety exactly. And then the second part is choosing the geometric parameter. And we have two choices, theta and A. And in this case, I'm going to choose A because it's a little more directly related to mass of the part. And I'm going to leave it as A squared because later on when I calculate the mass, I'm going to want the area. It just skips a few steps in the algebra. Okay, now let's do the same thing for buckling. We're going to substitute in something with a factor of safety for a critical force, and then solve for one of the parameters that's nice and directly related to part mass. So do that independently, then with a partner, and then come back. Should just take 3 minutes or so. You can hit pause now. All right, so the first step is to recognize that we want the critical force to equal the F1 times the factor of safety. If that's true, we'll get exactly our factor of safety. So if we plug those things into our critical force equation, we get this. And then if we massage terms and solve for A squared again for consistency, for the same reasons, then we'll find A squared is the square root of 24 over pi times the square root of the force times the factor of safety divided by square root of the elastic modulus times h over cosine theta to the 3/2 power. Okay, now the last thing we're going to do is we're going to substitute these into an equation for the component mass, and then resolve any remaining parameters by looking at which value would minimize mass. So now we're not trying to exactly match something, we're trying to minimize something. So the first thing I'd like you to do is write down an equation for the mass of this leg, which will be half the mass of the component. And then take a look, substitute things in, take a look and see if there are any remaining free parameters, and think about what value of those free parameters would minimize the mass overall. So this should take a couple minutes to do independently, and then a couple minutes to discuss with your partner, and then come back. And you can hit pause now. All right, so the equation for mass is just the mass of this element, and where this subscript S is mass dictated by stress. We're working from the stress equation here. The mass that's required is the density times the volume, and the volume is the length times the cross-sectional area. And we know that L is h over cosine theta from geometry, and we previously figured out that the area we need in order to meet our factor of safety for stress is this equation. If we plug those things in, we get this total equation for mass of the component. And you'll see that we do have one remaining geometric parameter, which is theta. Now we want the mass to be as small as possible. And so if we look at the right-hand side here, we want cosine theta to be as big as possible since it's in the denominator. And the biggest possible value of cosine theta is 1, and that occurs when theta is 0. So this is telling us that mass will be minimized if the angle of the leg is 0 and the height of our square cross-section beam is the square root of this term. Perfect. So we've we've optimized both of the geometric parameters in our component. Now, it may instead be that we need to design a part around buckling failure. So that will work exactly the same way. Here we have a squared set by the need to exactly hit our factor of safety in buckling. And you'll do the same thing. Write down the equation for the mass of the part, and then massage terms and look at which values of any remaining parameters would minimize mass, right? So take a couple minutes to do that yourself, then compare notes with your partner, and then come back. Hit pause now. All right, so once again, we'll have that the mass, in this case due to buckling, that's the subscript, is the density of the material times the volume, and that's the length times the cross-sectional area. We have the length is h over cosine theta, and the area is going to be set by this equation we derived from the need to exactly hit our factor of safety for buckling. And if we substitute those things in and massage slightly, we'll get the mass of the component dictated by the need to avoid buckling is this constant times these material terms times this loading term times this geometric term where h we can't choose, that's part of the problem as it was set up for us, divided by cosine theta to the 5/2 power. And once again, we're going to see that we want the mass to be little, and cosine theta is in the denominator, so we want cosine theta to be big. The biggest it can be is 1, and that happens when theta is 0. So once again, we have identified the mass optimal values of both of the parameters that define our component. Theta should be 0, and a squared should equal this. Now, you notice we've solved for those geometric parameters 2 different ways. And which one should we really use? Well, we need to use the bigger of the 2 to avoid failure. If we chose the smaller one, then the other failure mode would kick in before we hit our factors. And which one is going to dominate is not such a straightforward thing to answer. And it will depend on the quantitative values of our problem scenario. So one way to figure this out is to divide the mass, or we could also divide the cross-sectional area dictated by stress failure by that dictated by buckling failure. And if we do that and simplify, we'll find that the ratio is this. And we can look at this and gain some understanding of why that's the case. So first of all, if we have, let's do something that's easy. If we've got a high elastic modulus, that means that the material is stiffer and it's springier and less likely to buckle. And in those cases, the stress dictated size is likely to dominate. And for very similar reasons, if the yield strength is really high, then you need less cross-sectional area to avoid yielding. And because the cross-sectional area gets smaller, then buckling becomes more of an issue. If the force gets really high, then once again, the cross-sectional area gets big, buckling becomes less of an issue, and the stress-related mass dominates. If the height gets really tall of where that force is applied, then that we have an L squared in the denominator of that buckling equation, and the buckling is going to dominate. And which will matter the most in the case of this problem? This would be a time to add some actual numbers. But we don't want to lose sight of one of the big messages that has come through along the way. Notice that in both cases, both failure modes, our analysis told us that we wanted theta to equal 0. That was where the mass of our component would be minimized while exactly hitting our factor of safety. And that might indicate some qualitative changes to our component. So what I'd like you to do now is, thinking about this, go back to our original problem scenario, and we're going to go back to step 1 and generate some more candidate shapes. And generate, again, 5 or 10 candidate shapes. Do that independently first, then discuss the results with your part, and then come back. And you can hit pause now. All right, then hopefully you remembered in that process to keep it simple. Try not to add a lot of complexity as you try new shapes, and to reflect on all the things we've learned in that process. So here is one candidate shape. This is a simple vertical element. It's got a uniform cross section as you go up and down, and that is one way to accommodate this theta should be 0 message from our previous analysis. Instead of making something very complicated with two separate legs next to it, why don't we just merge those features into one thing? Great. And then I've also decided to make this a thin-walled tube. And why would I do that? Well, I noticed that there were two failure modes that were concerning as we did analyze that last part. There was stress related due to axial stress, and there was buckling. But I only had one geometric parameter that I could use to avoid them. And so by having a thin-walled tube, then maybe I can use one parameter to address axial compression, stress, and one to address buckling. And we'll see how that works a little later. So now let's analyze it. First, we'll create a free body diagram. And here's a candidate free body diagram, pretty fast to generate. And what I'd like you to do it now is take a moment and run this through your checks to see if it looks like it may be an okay free body diagram. And remember, the first one is static equilibrium. So can we achieve static equilibrium with this free body diagram? And hopefully you see right away the answer is yes. If the force here is equal and opposite and collinear to the force there, then you have a two-force member, and the sum of the forces in the vertical will be F minus F plus F, 0. There's no forces in X. And if we pick any point along this line to do moment balance, that will equal 0 because the leverage will be 0. So that's okay. How about deformation? How would this thing squish when you apply that force? And you can pause if that helps here to think these things through. So if you push on the top of that tube, well, you would expect it to move in the direction that you're pushing, and this whole thing would get a little shorter, and maybe it would squish in other ways. But the fact that you have this axial displacement is consistent with the idea that you have an axial force, and you really don't expect much other displacement to happen. So both of those things are consistent with this candidate free body diagram. And if you were feeling unsure still, you could throw it into FEA and do a sketch analysis, but I'm feeling okay about this one. So now let's generate our stress equations for this component. So take a moment, write down an equation for stress, the peak stress that you expect to find in this part, and it should have stress and some geometric parameters and loads on the other side of the equation. All right. Again, you can take a minute or two, then discuss, then come back and hit pause now. All right, so this is pretty straightforward, just like the last time. The stress is force over area, and in this case, it's the force over 2 pi RT. That's our equation for the cross-sectional area of a thin-walled tube. Great. Now let's write down our equation for the critical force for buckling. Same thing, take a moment to yourself, a moment with your partner, and then come back, and you can hit pause now. All right, so we'll have our classical critical force equation. It's equal to C pi squared EI over L squared. L, very straightforward. It's the height of that force application point. I will be determined by the cross-sectional geometry. And then C, well, we have a very similar situation as the last time where one end is fixed and the other end is free. And so that gives us our lowest possible value of C, which is 1 over 4. Okay, now we'll invert these. And the idea here is that we're going to substitute in something for stress to get exactly our factor of safety, and then solve for one of the geometric parameters. And we're going to pick a parameter that for which the mass will uniformly increase as it increases. And the simpler the relationship, usually the better. So do some substitutions and then manipulate things, do that independently, compare with your partner, and come back. Hit pause now. All right, so we want the stress to equal the strength of the material divided by the factor of safety. So we plug that in and rearrange, we'll get what we want. And in this case, I chose the thickness of the wall. because it's linearly related to the mass of the part, and also because we'll see a little later in the problem, solving for the radius for a different purpose will be convenient. But either way, it would work fine. Okay, and let's do the same thing for buckling. We're going to set the critical force to be what we want it to be, and then solve for one of the geometric parameters. Note that we've already solved for the thickness, so might be a good opportunity to solve for a different geometric parameter. So take a minute or two to work on that yourself, compare notes with your partner, and then come back. And you can hit pause now. All right, so we know that we want the critical force to be equal to the force that's applied times the factor of safety. And then we're going to solve this time for the radius, because we solved for the thickness previously when we were addressing stress. And part of our strategy here was to be able to separately meet our factor of safety for stress and buckling. So if the radius cubed equals this, then we'll exactly hit our factor of safety for buckling. All right, so now we'll go to our mass optimal parameters. And once again, just as in the previous optimization step in the last design, we're going to write down an equation for the mass. Then we're going to substitute in the value that we solved for previously. And then we're going to see what values of any remaining parameters will minimize mass. Right? So you can do that now, do it independently, then discuss with your partner. A couple minutes for each step, and then come back. And please hit pause now. All right, so the equation for the mass is just going to be the density times the volume of our part. The volume would be the length times the cross-sectional area. And we're again using that thin-walled tube cross-section approximation. And if we substitute in T, we get this, and then we reduce. Notice that we've got an R on the top and the bottom, and it falls out. And what we're left with is that the mass equals the density times the length times the force times the factor of safety divided by the yield strength. And it doesn't matter what R is at all, as long as T is this function of R, then this is the mass we're going to get. It's fully defined. And this happens sometimes. And you can sort of intuit this by recognizing that the stress is dictated by the cross-sectional area and the mass is dictated by the cross-sectional area as well. So great. We now know for this design exactly what its mass is going to be. But we don't yet know what value of the radius we should pick. And so let's go back to our buckling condition and use that information to find the value of the radius that we need in order to exactly hit that factor of safety. And the way we're going to do that is combine our two equations. So take a moment and combine these equations and solve for R. Just a little bit of algebra. It should take 1 or 2 minutes. You can do it independently and then discuss with your partner and then come back and hit pause now. All right, so if you plug this equation into this one, you get this, and then if you simplify, you'll get this, and then if you massage things a little, you'll find that the radius should be 2 times the square root of 2 divided by pi times this material term, the square root of the yield strength over the elastic modulus times the length. And this is awesome. So if we set the radius to equal this, and then we set the thickness to equal the implied value of thickness, we know exactly what mass we're going to get, and we're going to exactly hit our factor of safety in both failure modes. And at this point, we probably feel pretty good about our design. We understand the potential failure issues in this space. We've picked something that exactly meets our desired factors of safety for each. We know that we can't make the mass any lower for that yield strength failure criteria because, well, you just need a certain cross-sectional area, right? And you need a certain length. And so at this point, we might feel like we have a pretty good argument that this is about as good as we can do. And we should move on to designing some more detailed features like how this force interfaces with this tube. All right. Now, those are a couple of examples of coming up with candidate designs and analyzing them. But of course, if you look at your original sheet of paper, you probably had lots and lots of different designs. So the great thing is that no matter where you start from, there will be messages that help you to move towards an improved design. So let's do a couple examples of qualitatively different sketches that you might have had and how you would have figured out that there are features in them that were undesirable. And let's take this as an example. So I want you to imagine that this was one of your first sketches. I want you to mentally walk through that process of analyzing this part and see where along the way would you have gotten the message that, oh, there's a feature here or something qualitative about the part that is going to be less than optimal that I should change, right? So I want you to mentally walk through that process by yourself for a minute or two, then discuss it with your partner, and then come back. And you can hit pause now. All right, so there's lots of ways that you could have figured this out, of course. Certainly for the angle of these legs, we could have identified that that's suboptimal using the same process we used for the inverted V. But what about this little bit in the middle, this the crossing on the A? Well, there are a few places that might show us that something, that maybe that little cross isn't needed. For example, in our free body diagram, we might notice that the force seems to point straight at the load application point. Doesn't seem like a force needs to pass through that middle part. That's not always a correct conclusion, but it might be an indication in this case. If we draw the deformed shape, we'll see that that crossbar does not need to change length very much in order for this top part to move quite a long ways in the distance of the applied load. And remember that the amount that it stretches is often proportional to the amount of force it has. So this small value of the displacement or the change in the length of that crossbar is an indication that it sees low force. We might also see it in our stress analysis stage. When we break this thing into pieces and try to come up with a free body diagram for each piece, a perfectly reasonable guess is that there's no force on this. It won't ruin any of your free body diagrams. And in fact, adding a force on that makes it a little harder to achieve static equilibrium for those two legs. So there's another indication, maybe I don't need that piece. And if we do a sketch FEA, we'll see all this material is blue. If we looked at the scale, we'd see that indicates almost zero stress in this case. And so yet again, this material is probably not pulling in weight. It's unstressed. So you want to be on the lookout for signals from your analysis that you have a feature in your design that's not helpful. And you want to avoid complicated ways of addressing that problem. In this case, we'd say just don't have the crossbar, and eventually we want to merge those legs into a single vertical element. But we wouldn't want to say, oh, let's add another leg in the middle so that that crossbar does see some force. That wouldn't be a good solution. Try to keep it simple. All right, here's another example. Let's say that this was one of our original sketches. Imagining yourself walking through that design process, analyzing this candidate design, where would you catch that this shape is not likely to be mass optimal? Take a moment to think about it for yourself, then discuss it with your partner, and then come back. And you can hit pause now. Okay, once again, lots of ways this could happen, but one place is at the stress analysis stage. So let's say we have our free body diagram that says there's a force down in the center and a force up at the center of the bottom. So it's a two-force member and it's axially loaded. Then we just have that the stress is going to be the force over the area. But our area is changing, notice, as we go from the top to the bottom. And so it's at the top, it would be force over the thickness times little a. At the bottom, it would be force over thickness times little b. But in both cases, we would like that stress to be equal to the yield strength divided by the factor of safety. So if we plug those equations in, we'll find that A should equal F times FOS over SY times T, and we'll find that B should equal F times FOS divided by the yield strength times the thickness. And therefore, they should be equal to each other. And that's saying we don't want a trapezoid, we want a rectangle. So those are a few examples of how doing this quantitative analysis with symbolic algebra can actually show us that we need to make qualitative changes to our design, that a different shape would be better. And in fact, pointing us towards what those shapes might be.